y equals 2, you reflect it across that line right there, where y equals 2. That line, there it is. You get y on itself, y prime. You get t down here on the x-axis. You get I up here. Something like that. So you could write like reflection across the line y equals 2 of xy equals, you know, another way to write it would be like with the coordinate rule, just saying xy arrow. Anything you got so far? Notice? Anything staying the same?
The y.
The y value, yeah, it's not going up or down, so what's going on with the x? Are you sure the y is not changing? Isn't it moving up and down and not left and right?
Oh, true.
Seems like the x isn't changing. So here's what I might do is look at like y goes to from 0 on the x, 2 on the y, goes to y prime. Okay, that's not very helpful because it just stays the same. Maybe it is helpful. That seems like nothing's changing, but t goes from negative 1, 2, 3, 4. Negative 4, positive 4, to t prime, what do we got? It's on the x-axis now, right? Negative 4 on the x still stays the same, but now 0. Kind of tricky. If you remember from last week, we go opposite y when we're reflecting across the x-axis, which is still kind of true. We're gonna, all this stuff's gonna go negative for sure. There's kind of some weird stuff going on here though, right? Where with the stuff we just did. So for example, I'm not going to negative 2. We actually just stay the same, right? If I did flip y over the x-axis, it'd go down here to negative 2. Then I got to adjust and move it up 4. So that would be one way to write it. And you could say the same thing here. How you doing with x equals 1? Z is 2 units away. D is 4 units away. Prime notation, 2 units. Notice M and Z, we still have vertical line there. They're the same x coordinate. M prime, Z prime, same x coordinate. D prime, one diagonal there. Something like that. Nice. What do you got for coordinate rule here? You could write just like xy arrow, or you could be like reflection across the line, x equals 1 of xy is going to give me, what's staying the same here? The y. Yeah. And what's going on with the x? We're going opposite x. Excuse me. Z is at 1, 2, 3, 3, 3, 3. It goes to z prime. Negative 1, 3. So yeah, the y doesn't change. Similar thing happening. All this stuff's going negative. So we're going to have a negative x. Then we got to adjust for it. So instead of negative 3, we're at negative 1. We're adding 2 to that. So look at M. M goes from, it's the same thing. When I look at D, just a different one. That's a different x coordinate. P, let's look at D. D goes from 5, 4 to D prime, which is way over here at negative 3, 4. So if I go opposite x, I go negative 5 and then add 2 would land me at negative 3. Alright, well you take, open your Chromebook if you haven't done so, and go to the reflections document. How'd you do on these? You got coordinate rules? Kind of similar to what we just did. 1, 3, got A. B is at negative 2, 1. And C is at 3, negative 2. Alright. Might be. So reflecting across the line y equals 1, really similar to what we just did, right? Notice B stays the same. A is going to be 2 units away from, so think about what's going to stay the same here, reflecting over a horizontal line. Going to get like A. So A's at 1, 3. It's 2 units away. It's going to be 2 units away. A prime, 1, negative 1. B stays where it is. So notice we're reflecting across the line y equals 1 and y equals 1. So it's going to stay there. And C, the prime notation on all that. C prime. Okay, C is 3 units away. It's going to be 3 units away on the other side. So we get this triangle here. C prime. 3, 4. So now we're not moving it in any direction. Sorry, we're not moving it left or right. So the x is staying the same. What's going on with the y? Check with your neighbor on those rules. How you doing? Your table. Least number. Make sure y'all got something. Carson, how'd you get that? With an opposite y.
Plus 2.
Plus 2. How'd you figure that out?
Well, I just did a and then a prime. A is 1 comma 3, and then a prime is 1 comma negative 1.
Yeah.
So if we change the y to opposite, so then it's 1, -3. To get to 1, -1, you add 2 to it.
Awesome. Yeah, for me, I'm kind of thinking like trying to generalize here what's going on with the coordinates. All these positive coordinates are going to go negative. So that's kind of helping me think, okay, that's where we're getting its opposite y. And it is really similar to reflection across the x-axis, which I hope you noticed was xy goes to x opposite y, right? We just get opposite values reflecting across the x-axis. Nice. How about reflecting across the line x equals -2? Oh my gosh, b stays the same again. A, 3 units away, 3 units away for a prime. C is 3 and 2 more, 5 units away. Did I give you enough room here? Just barely. Something like that. Funky business. Once again, B prime is the same, huh? So A prime, what's changing this time? The X value, right? It's not moving up or down because we're reflecting across a vertical line. So -5, 3, A. B prime stays the same. -2, -2, 1. Notice again, x equals -2, and that's the x coordinate of B, so that's why it's not changing. C prime, way over here at -7, -2. Coordinate rule here, x, y goes to x, actually, x is changing, right? X something, 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 comma, y. I know that y isn't changing. Did you get something here? Notice, so maybe a little bit tricky if you get too close to that line of reflection, but if you look at all the positive x values, they're going to flip over and become negative once again. Opposite x. What else do I got to add? Or subtract? Did we do it? Subtract 1. Interesting. Well, so notice the line of reflection is at x equals -2, right? Notice -2 stays at -2 for the x. 1 goes to what? -5. So I got, if I'm thinking opposite x, I got -1 and I got to get it down to -5. -3, we got to take it to -7. Opposite of -2 is +2, and I want it to come back to -2. Another thing you could do is look at what happens to 0. Because if I do opposite 0, it just stays 0. So any point on the y-axis would flip over to -4. Does that help you see that you got to subtract 4? Nice. How you doing with y equals x? All these points are going to change, huh? Did you get a prime at 3, 1? Getting a little messy here. The line y equals x, slope of 1, y-intercept of 0, what you might call a parent function for linear functions. Here we'd be counting diagonal distance. I want straight to the other side. And so, erased a, there's a prime at 3, 1. B prime is 1.5 diagonal, so 1.5 diagonals on the other side would be B prime. And C is 2.5 diagonal, so a half, 1, 2, and there's C prime. So B prime ends up at, right here, at 1, -2. And C prime ends up here at -2, 3. Anything you notice going on there? Kind of weird rule, scares me to write it like this. Because people mix up the x and y coordinates all the time. You Get that? Yep. Sweet. Okay. What about reflection across the line y equals negative x? Ooh, that's nice. A prime is a half unit away from the line of reflection, just like A. Oh my gosh, so is B. This one worked out pretty nice. So y equals negative x, got a slope of -1 through the origin. Oh, that's not A, that's C, isn't it? Yep, sorry about that. And that's A, here we go. A is 2 units away diagonally, 2 units away diagonally to get C prime, A prime. There we go. Alright, so A prime. You get it at -3, -1. You can kind of see some things happening here maybe. Like all the positive x and y values in the first quadrant are going to flip over and become negative. Some other things going on there as well. It's not just changing sign, because in like the second and fourth quadrant, it actually stays the same in a sense, right? It stays in the second quadrant. Points in the fourth quadrant stay in the fourth quadrant. So B prime ends up at -1, 2. -1, 2 right there. And C prime ends up at 2, -3. Coordinate rule here, x, y goes to, so you could write this also like this. Probably a little more cumbersome. Of course you could just copy and paste this. Y equals negative x of xy, the same what we're doing in general here. You got a coordinate rule? What did you get?
I got negative y, negative x.
Nice, yeah. So we're switching them and they go opposite sign. Awesome. Nice job. Okay. So remember the key here is that the line of reflection is the perpendicular bisector to the line segments connecting corresponding vertices. What? The line of reflection, in this case the blue line, is the perpendicular bisector to the lines connecting corresponding vertices. So it cuts the green lines that I've drawn here in half at a right angle. That's what it means to be a perpendicular bisector. So use that fact, try to find the line of reflection on, and see if you can write, what it is in a fancy way. I believe you can click on the graphs and edit them. That is the whole idea there. On the one, well, you don't have to edit that one, you can if you want, if it's helpful, but that one is what I really want to do. That one works, sweet. Composite. So what I was trying to say is if I connect corresponding vertices, the line of reflection is the perpendicular bisector. So if I found the midpoints of all those lines, if this is indeed a reflection, the line of reflection goes right through the midpoints of all those red lines at a right angle. Did you find it? Did you find the midpoints? Like right there, right there, right there. Okay, so the line that goes through those, So how would we write this? You could do equation editor. You could use subscripts. You could, just get some practice, maybe thinking about this as a function. We're saying we're reflecting across which line? Y equals x. And then you could say of A, B, C, D is what's going to take us to the image of A, B, A prime, B prime, C prime, D. Least number, check with your table on the next one. How are you doing? What'd you write for that? Nice. Boom. That's probably enough. Oh, nice. How do you know what it looks like? Kind of visualizing it. So if you connect B to B prime, the one goes through that midpoint. If you can figure out where that would be. Right. Ooh, coordinate rule on that next one is real tricky. Don't necessarily worry about it. Least number, your table's good? How's your table doing? You got it? Uh-oh. Leaving them in the dust. What'd you get here? You can click on it to connect corresponding vertices. Nice. Corresponding vertices would be like B to B prime. If I connect B to B prime, D to D prime, A to A prime, it's going to go right through that line I just drew to C, to D. Nice thing, C to C prime. Those are on the same coordinate. So I know it's going to go through the origin because C and C prime are on the same point. And if a point reflects to itself, that's because it's on the line of reflection. And then looking at midpoints, notice from D to D prime I'm going down 4, right 2. So midpoint's going to go down 2, right 1. Really, exact same thing for B. And there it is. I got 3 nice points that could help me find the line of reflection. Draw a nice line there. Boom. What is this reflection? I'm not expecting you to come up with a coordinate rule for this, by the way. It's really tricky. So you just looking for what's this a reflection of. Again, we could say ABCD goes to ABC prime, ABCD prime. What is that line of reflection? So I'm just looking for the line of reflection. Don't worry about the coordinate rule here. If you come up with a coordinate rule, tell me. It's super tricky. What'd you get for, what's this reflection, Mindy?
Oh, sorry, it's not letting me load.
Y equals, what's this line? Y equals,
Sorry,
the equation of the blue line.
Oh, 1/2 x.
Y equals 1/2 x plus 0 minus, yeah. All right. Nice job. Okay, so there, ooh, a glide reflection. So this is kind of like another type of transformation that's a combination of two rigid motions that kind of produces something a little bit different than just a reflection or just a rotation or just a translation. It's called a glide reflection. All of these things sometimes are called isometries. Iso meaning equal, metry like measured, so it keeps them the same. So it's kind of another way to look at it, I suppose. So we're looking at PQ, just this line. So with this glide reflection, we're first translating it along the parallel to the direction of the line of reflection, along the line of reflection, and then reflecting it. Cool with that? Notice how the composition is written. So I've got RK, what does that mean? Reflection across the line K. And we got this circle thing. Have you seen this before? Seen the circle thing?
Wouldn't it be like composed those?
Oh my gosh. Yeah, we're composing functions, exactly. Yeah, remember that? F composed with G of 0. What do you do here first? How would you do that? Personally, I would write it F of G of 0 to remind me to do the G first, right? Really similar thing here that's easy to confuse. And again, if you really wanted to, no reason why you couldn't write parentheses. Reflection of this translation. So I wrote AB like we're moving left and right A, up and down B, of PQ, and that's giving, and I've written it as PQ double prime, indicating we're doing like two things to it. With the glide reflection, does it matter the order that you do things? So we've learned with compositions it does, right? But what about with a glide reflection? Why are you saying no, Jack?
Well, I was just thinking about it, because if you like slide it down and then flip it, it would be the same if you flip it and then like slide it down.
Right. Yeah, in this case, PQ's the blue line, sliding it up and then flipping it. We'd end up with the same thing if we flipped it. Maybe use a different color. Flipped it and then slid it in the same direction, right? So the glide reflection is kind of nice because it doesn't matter which one you do first. Awesome. Good thinking. So I was thinking, you're welcome to draw this out if you want to do it by hand. I have no problem with that, just a little more work maybe. But my thought was click on it, edit it, and show the glide reflection of lux. So I might look for this line of reflection even though technically I should be doing the translation first. Nothing wrong with that, but x equals 1 is a vertical line. And notice the direction of movement is, I'm not going left or right. So t is 0, translating 0 units left or right, 4 units down, right? The vector, this vector 0, -4 would look like that, right? Just going straight down 4 units. Make sure your table's good, least number in charge for the day. Ooh, nice. It would be great if you could label vertices double prime notation. Ooh, love it. Yeah.
Question. For the light reflection, there are cases where that statement doesn't hold, right?
Where it does matter which order you do it.
Yeah, because if you translate it onto the line, I don't know how to explain it without drawing it.
So if I moved it to the right and then flipped it.
So I was thinking if you had a line like this and an object right here, if you flipped it and then moved it up, it would be different from if you moved it up and then flipped it.
Nice. Yeah, that statement is not always true. What makes it always true is that we are translating it parallel to the line of reflection. So that's what needs to be true, right? So yeah, you could write in that box asking you about that. Order does not matter as long as the translation is parallel to the line of reflection. Yeah, you're absolutely right. If instead we're like moving PQ left and then reflecting, that would be different than moving reflecting and then moving left. Totally. Yeah, moving left would like take it over here. Reflecting it moves it way further way over here. If I move it, or if I reflect it and then move it left, then I end up with something like that. Yeah, nice. So the condition needs to be that the translation is parallel to the line of reflection, which hopefully we see is true here, right? Technically what this is telling me to do is move lux down 4 units. So x prime would be at 0, 1, u prime -3, 1, and L 4 units down, L prime, and then reflect it. But if we reflect it and then move down, in this case we would end up with the same figure. So we should end up with that one, right? How about a coordinate rule? Anybody come up with that? I think this one's kind of interesting. What's going on with the x? Well, the x went from 0 to 1. All this negative stuff went positive. We're getting that opposite x thing going on. And then we got to adjust it because it's not the y-axis. We actually got to end up at 2 here. -3 ends up at 5, so it doesn't go to +3 but 5. We got to add 2 to adjust to it. And then what about the y? The y is changing. We're sliding down. We're sliding down 4. Oops. So we would say y -4 would be the coordinate rule for that. I didn't ask you for that, so it's all good. But kind of interesting writing a coordinate rule for a glide reflection because we're moving parallel to the line of reflection. We see a translation. on the y here, and a reflection on the x. It's all good if you don't write that down. How about this one? Y equals negative x. Oh my goodness. Okay, if we're not moving along the line of reflection, it matters, right? We got to translate first. But this is telling me to go left one, up one. So boom, L prime. Everything just moves diagonally to the up and to the left 1 unit. Not so bad. And then we reflect it. Coordinate rule for this would be a little bit different. Definitely, if you're up for the challenge. L prime, G prime, and Q prime is 1.5 units away. And I should be writing double prime because we've moved it twice. So that is a composition of transformations, really similar to composition of functions, and written very similarly. Again, if I flipped it and then translated it, notice the coordinates are 1 diagonal away. Would have ended up like that. But like Jeffrey's saying, that's not always going to be the case, and we'll see soon. Doing a composition of different transformations, we can end up with different things. The order does matter, and maybe counterintuitively, we're going to go from right to left, the thing closest to the input. All right. Sorry if it feels like we're rushing here. I know. Lines of symmetry is what we're ending on here. A figure in the plane has line symmetry when the figure can be mapped onto itself by a reflection in a line, like a butterfly. And almost like all animals have line symmetry. Is that true? I think there's a name in it in biology. Anybody know? Anyway, a figure can have more than one line of symmetry. That's cool. How many lines does each hexagon have? So I think my idea was drawing it in, but you can just write how many do you see here? Is that all? Are there just 2 lines?
Can't we do diagonal?
On this one?
Yeah, can't we do it from
Like that? Okay, where would that go? Up here. Right?
Sure.
So it's got to map to itself. Like, how about C? Would these points map to other points on the, yeah, there's 1 here. That's it, right? Okay. Maybe you're jumping ahead of me. How many do you have on B? Oh gosh. 1, 2, 3. Is that it?
There's 12.
There's 12 lines?
No.
I don't know about that.
Or
4,
There's 6.
5, 6.
There's 6. Nothing.
You were
I double.
okay. Want you to finish with those words. Check it out. Want to figure out shortest way to computer B with extension. If you flip computer A over, the line that goes from A to B and that reflection will be the shortest distance. Pretty cool stuff. Application, boom. Please finish reflections tonight. We were so close. All you gotta do is look at those words. Word symmetry. Symmetry everywhere. Look around, see it. It's everywhere. And find out what biologists call it. Science class. You got a question? Thank you. Good. See you tomorrow. It'll be a weird day.
Wait, why?
Tests. There's tests.
Is it a math test tomorrow?
I hope not. We got